Instead, what I want to do is get started on letting you know again that we have a midterm next week on Thursday. So 1 week from right now is our second exam. It will cover everything that you just studied for the quiz, which is good because you've got it fresh in your mind by now. But also the other part of it will be the stuff on continuous functions. That's 4.1 and 4.2. So there'll be just a little bit more coverage for the exam next week, but you also have the entire class period. So next Thursday, you'll take the entire class if you want to. I'm going to do a couple of study sessions, review sessions next week on Monday at 7 p.m. and also on Wednesday at 4 p.m. I'm going to do these sessions in the room right outside of my office, which is MH33. I will also have my camera with me, and I will, if you want to join via Zoom, you can do that. Or if you can't make it at these times, but you would like to still be able to watch it or at least get something out of it, I will make a YouTube of it. I'll get the recording of the videos and then I'll send the YouTube links out to you. So you'll be able to watch those because I know not everybody can make it at every time that I would put. So the first review, obviously, I'll try to go hard and heavy on that one. And then on Wednesday, if there's some things that I overlooked or didn't get a chance to really do justice to, I'll hit those on Wednesday and then maybe cycle back on Wednesday to the really important stuff and give it a second look, kind of review some of the same stuff we did on Monday. So between the two reviews, that's 4 hours of me talking about 7 sections of material. I ought to be able to cover that pretty well, at least have some good examples there. By the way, also included in this material is the stuff on those notes you took on limits involving infinity. There was quite a number of people who did not, with the homework that you turned in on Tuesday, who did not attach their notes for the video. I'm not sure if you didn't take the notes or if you just forgot to attach them, but I didn't see them from a good number of you, so it might have just been a miscommunication on my part. But anyway, if you haven't watched that video or you don't have those notes somehow, you should do that because I will be thinking about questions that could involve limits involving infinity. In fact, you'll see on next week's homework that there are some examples like that. I forgot to mention homework number 10 is due on Tuesday. I would try to get started on this one as soon as you can so you can start focusing on the big picture of the exam. There are about 8 or 9 problems on this assignment, just very similar to the last assignment. So it will take a little bit of time, but I think it'll be good practice for the midterm as well. So I'll have lots of office hours. I'll be emailing you over the weekend, reminding you about the review sessions, and I'll throw in some extra office hours next week. We'll try and hit it pretty hard as we head towards spring break. That's kind of where we're at. Any questions about any of that? Okay, no worries. Don't worry about this theorem here. I'm going to use it in a few minutes. I just wanted to have it on the board so I could reference to it. What I'm going to do today actually is start a new topic, and it's actually a new section that won't be on the exam. So I've already covered, this is one thing I'm very happy about. I've already covered all of these sections. So we're a week out from our exam and all of that material has been covered. So I'm going to start a new section today that won't be on your exam next week, but of course it'll eventually be on an exam. And you'll see that we're going to still be using a lot of the stuff from those sections. So I think it'll be important. So this is section 4.4. I think it'll be helpful to go on and try to cover this here. And this is going to be, the title of this, guys, is Consequences of Continuity. Consequences of continuity, like what can we do with continuity? And these are some very, very important results. I have about 4 or 5 of them actually. And I am hoping I can get through most of this today. Let me go ahead and state the first one right away. And this is proposition 4.8. As always, I don't expect you to memorize the numbers of the results, but I will give you a little bit of a nice description of this result so you can think of it this way. This result is going to be called boundedness of continuous functions. Okay, so we'll call this boundedness of continuous functions, proposition 4.8. And here's what it says. By the way, most of the nice thing about most of these results today is they're very easy to write down. They're just short, simple statements. So here is the statement of proposition 4.8. If f is a function from the closed interval AB to the real numbers, and since we're talking about consequences of continuity, you won't be surprised that I'm going to assume that this is continuous. And I'll just say continuous on the entire closed interval AB. So it's continuous throughout its domain. Then, so if we have a continuous function on a closed interval, then f itself is bounded on AB. And I think I talked about this when we were doing some of the homework on Tuesday. What does it mean for a function to be bounded? I just mean that the range of f, this would be the range of this function, which is a subset of R, right? The outputs of the function, they should form a bounded subset of R, right? So in other words, the range of f is a bounded subset of R. So that's essentially what that means, okay? I'm going to do the proof of this in just a minute. Let me just give you a little of the intuition behind it first. So I have just a picture to kind of, pictures are always good for intuition. Maybe I have my x-axis here, and there's a closed interval from A to B that I can kind of draw as part of that x-axis. And my function is defined on this entire closed interval. So that means that there's a value of f of A somewhere, and there's a value of f of B somewhere, and the function is continuous. That means I should be able to get from point A to point B without picking up my pencil, right? So I can, just draw this thing, and it might go up and down a lot, but it should be possible to draw the entire graph without picking up my pencil. And if you can do that, then you can see that the function, the range of that function is bounded. There is a, sort of a ceiling here. I might call that B. And then, of course, the negative of B would be down here. And within that horizontal strip, the entire function exists, right? So that's kind of the way to think about this result, okay? Now, I should point out as a remark, again, before I do the proof, as a remark, that this result is not true for open intervals. Okay, so the result, so this proposition fails for, let's say, the open interval AB. And I'm sure that what you would want to see is an example of that, right? And I'm just going to make a little picture to show this example of this. So I can have a continuous function on an open interval. Let's define f to go from the open interval 0, 5, just picking 5 kind of randomly, to R via f of x equals 1 over x. So of course, f is not defined at 0, but I'm not including 0 in my domain here. And if we actually think about what this graph would look like, here's 5 right here, and 1/5 would be right here. And so the graph would get to that point. But what you're going to notice is that this graph shoots up to plus infinity. Okay, so the range of this function is not bounded. As a subset of R, it actually is a ray that extends from 1/5 all the way up to infinity. It is continuous. We proved that. This is continuous at every C that's not 0. But as it turns out, it is not bounded. So we have to have a closed interval for this proposition to be true. And what that means is that as we're doing this proof, just make sure I have my volume up here. There we go. What this means, guys, is as we're doing this proof, we should pay attention to where we actually need the interval to be closed. Because clear the proof isn't going to work if it's an open interval. Okay, so let's try and do the proof. I think that's the next thing, right? Write down the statement, we give a counterexample if the assumptions don't hold, and then we give the proof. Okay. So here we go. We're gonna do this proof, guys, by way of contradiction. We're gonna do it by way of contradiction, which means I'm gonna assume that F is not bounded. Okay, so let's do that. Let's assume that F is not bounded. Okay, and what this means is that we can look at the range of F as a subset of R, and it will be unbounded. There is no B, there is no ceiling to the outputs of this graph. So what we can do is, in this case, I'm actually going to make a sequence out of this. I'm going to say for all natural numbers, there exists a sequence. I'm going to call it Xn. And these Xn's are in my domain, so they have to be in this closed interval from A to B, such that if we look at f of Xn, f of Xn, that let's just take the absolute value of it so we don't get into issues of this thing, because it could be going towards minus infinity. But the absolute value of f of Xn is going to be greater than or equal to n. So what that means is that I can find an input x1 whose value would, for which f of x1 would be more than 1. And then I can find another point x2 for which f of x2 would be more than 2. And then I can find another point x3 where f of x3 would be more than 3. And I can do this forever, right? If f is unbounded, I would be able to do this forever. There is no b ceiling here that we can't find an f value that's above it, right? So if I keep redrawing a horizontal line at any value of n, I'm going to be able to find a place where my function is above that horizontal line. Does this make sense? Yeah, so this is really the key right here. Now, I'm eventually going to look at this list of values f of xn, but I'm going to first just look at the xn's. The xn's, although the f of xn's are not bounded, the xn's certainly are. They are within this closed interval, and we have a theorem that I believe you just wrote down on the quiz called the Bolzano-Weierstrass theorem for sequences, that says that if you have a bounded sequence, it must have a convergent subsequence. Did you guys all get that right? Yes, 100%? Okay, I hope so. Anyway, so that's one of the most important theorems. So I'm just going to say by the Bolzano-Weierstrass theorem, or the BW theorem if you want to abbreviate it, but by the Bolzano-Weierstrass theorem, since the sequence xn is bounded, everybody agree it's bounded? It's within this closed interval on the real number line. So it's not going off to infinity or minus infinity. So that sequence is bounded. There exists a convergent subsequence, and I'm going to call it xnk. We don't know much about it, but it will have to exist. And it, of course, has to converge to something. Let me just say that it converges to x. Okay, so xnk converges to x. Can anybody tell me anything that they know about x? It has to also be in that closed interval AB. That was another one of our theorems. So by theorem 3.3 is the number of it. Again, I don't really care that much about the numbering, but just for your own referencing, by theorem 3.3, x is also in that same closed interval. Right? Now, see, that would not have been true for an open interval, right? So if the xn sequence had been in an open interval A, B, and then we have the subsequence in the open interval AB, of course, it might converge to a point that's not in that open interval. It could be like on the edge of it. I think you guys have given me examples of that already. So yeah, so we really are using the closed interval here, with the nature of that closed interval to make that work. Okay, so we have that. Now, guys, here we have a convergent sequence, right? Now I'm gonna use this result over here. You don't need to necessarily write the whole result back down into your notes again. But we are reminded that f is continuous. And that at this moment, we do have a convergent subsequence, x and k converging to x over there. And what does this theorem 4.1 say that we did about a week or so ago? It says that as long as you have a convergent sequence within the domain of your function, then if you take the image of that sequence under the function, it must converge to the image of C, right? So this is, so in other words, continuous functions preserve convergent sequences. If you start with a convergent sequence and you apply f to everything in sight, you end up getting a convergent sequence within the codomain of the function. So that's exactly right. So let me reference that result then. So by theorem 4.1, right? So by theorem 4.1, since f is continuous at x. Okay, so x is sort of the limit point of the subsequence, right? What we know, guys, is that the sequence f of x and k converges to f of x. So we would know that. Okay. So far, so good. But this is going to be a problem. This is going to be a big problem, guys, because these the fx and k's are not bounded. They're blowing up to plus infinity or whatever if I take their absolute value. So how in the world are they going to be converging to f of x? Like, this is going to be the contradiction. We're looking for a contradiction here, and we're just about there, right? So since convergent sequences are bounded, have a convergent sequence, it must be bounded. And here's my convergent sequence, right? So that means that my sequence of f of x and k's is bounded. It converged, so it has to be a bounded sequence. However, I'm going to tell you right now, it's not bounded. I just said it's bounded, and now I'm going to tell you that it's not bounded. How do I know it's not bounded? Well, let's look at how big the values are. Let's look at the size of or the absolute value of the f of x and k. Well, according to what we said at the very beginning of this proof, that's at least as big as nk. So whatever the subscript is the bound that we're using. And nk is, of course, at least k. Right? N1 is at least 1, N2 is at least 2, N3 is at least 3. And so this is saying that f of x and k is unbounded. And so we said it's bounded, now we're saying that it's unbounded, and that's the contradiction. It's bounded because convergent sequences have to be bounded, but it's also unbounded because the original f of x1, f of x2, f of x3, f of x4, those values had to get arbitrarily large, right? So that means that it's unbounded. Okay, and so this is a contradiction. This is a contradiction. We have two statements that are completely at odds with each other, and so it's a contradiction. Okay. What do we think? Is everybody okay with that? Question, Lindsay?
I don't know if this would be the correct way to think about it.
Mhm.
Because it kind of like that whole one-to-one technically, because n and k are natural numbers, and since the natural numbers aren't bounded, they're infinitely large. So
And the point is that this is like a strictly increasing sequence. So n1 is bigger than 1, n2 is bigger than 2, n3 is bigger than 3, and so on. So yes, in that sense, you can think of it that way. You're not necessarily looking at all of the natural numbers. It's a subset of them, but it's an unbounded subset of them. Absolutely true. Yeah. Okay, so that's the first result.
The
Pardon?
k. The greater than or equal to k.
Yeah,
Okay, you just pull it from there over. I just wanna know where the K came from.
Oh,
Yeah,
this is just a subscript for the subsequence. So when we make this subsequence here, we have xn1, xn2, xn3, and the K is going off to infinity, right? It's just the notation for a subsequence, we used a double subscript, which was usually a K value. And that K value blows up, yeah, absolutely. A sequence always has infinitely many terms. It's just that some of them might be repeated eventually, but not in this case. This case, these values are continuing to get larger and larger and larger. Yeah. Okay. What do you guys think? Not too long, right? That's pretty short proof. So it just gets better from here. One of the most important things that you would have done in calculus is you would have talked about extrema of functions, maximums and minimums. In fact, you learned how to find them by using derivatives and critical points and testing them for whether they, there's first derivative test or second derivative test to decide if they were saddle points or absolute maximums, minimums, or whatever. Well, now that we have this proposition, we can actually formalize that here as well. So I'm gonna do that as well. And so I'm gonna make a definition and then we'll state our second consequence of continuity. Okay, so here is the definition. I'm going to let f be a function from a domain D to the real numbers R again. Okay, so then f has an absolute maximum. An absolute maximum. And then in parentheses, I'm going to simultaneously define absolute minimum. So I'll say respectively. So RESP just is a shorthand for respectively, absolute minimum. So we're going to define both of these words in the same definition. At some point, x1 in the domain D. And then again, I'm going to go to the respectively. So that respectively is just going to be x2 is in D. So again, you either read the part that's in parentheses and go with that, or you ignore it and just read the part that's not in parentheses. So there's an absolute maximum at x1 or an absolute minimum at x2 if for all x in D. So I bet you know what I'm gonna say. If I have an absolute maximum at x1, doesn't that just mean that f of x1 should be greater than or equal to every f of x value? For everything in the domain, right? And then we'll have a respectively again. The respectively would be that f of x2 would need to be less than or equal to f of x. Okay, so if you prefer to write them out in your notes as two separate definitions instead of having all these parentheses separating the two parts, totally reasonable to do that if it's just easier to see it. But for saving some writing, that's why I did it this way. Okay. It's exactly the definition you would have seen in Math 150A. Essentially, an absolute maximum is just a value of x in the domain for which f of x is as large as it could be anywhere in the domain of the function. So f of x1 greater than or equal to every possible f of x. Okay, so no surprise there, really. Far so good? Of course, you would have learned in Math 150A that not every function on every domain even has an absolute maximum or minimum. They don't always exist. In fact, you would argue here that this function does not have an absolute maximum. There is no value of f that is larger than every other value because this function is going off to infinity right here. So this is not always going to exist. And of course, that's what my next theorem is going to, my next consequence of continuity is going to address that point. Is that a hand?
Yeah.
Yes, okay.
So is it possible if D is partial? So then
No, we are not going to be allowed to plug plus or minus infinity into our function. So D is, I hope I said it somewhere, a subset of R. It should be a subset of R. This is kind of assumed. Well, here I didn't really reference D here, but yeah, D is always just a subset of R. Yeah. Sorry about that. Okay, so with that in mind, let me state the next result here. This is going to be theorem 4.2. But again, I don't expect people to memorize these numbers, but I will give you a descriptive way to maybe think of it. This is going to be something that you probably have heard of. It's called the extreme value theorem. So we're going to state this extreme value theorem here, and then we're going to try and prove it. So here's what it says. Again, very easy statement, right? These statements are all very easy today. If F goes from the closed interval AB to R. So by the way, you might be making some flashcards for these, but I would not shuffle them into your stack until after next week's exam. This stuff is not going to be on the midterm. So at some point you'll want to know these obviously for an exam, but not for next week's exam. So if F from the closed interval AB to R is continuous on the closed interval AB. So you might notice that that's exactly how the previous result started. If F from the closed interval AB to R is continuous on the closed interval AB, then, so what are we going to say this time? This time we're going to say that F has an absolute maximum and an absolute minimum. It has an absolute maximum and an absolute minimum in this closed interval AB. Now, when I'm talking about absolute maximums and minimums, I'm talking about the x1 and the x2. This can be sometimes confusing in calculus if the students will be, asked to find the absolute maximum or minimum values. If I say that, then I'm actually looking for the f of x's, right, as opposed to just the x's. So you have two things here, guys. You have the x1, you also have f of x1. So when I'm talking about the absolute maximum and minimum in the closed interval AB, I'm obviously talking about an input into the domain of the function. So that would be the x1 or the x2. The f of x1 and the f of x2 are often called the values, the absolute maximum value or absolute minimum value. So it's just a little bit of terminology here. Okay, so let's see if we can start working on the proof of this one. Theorem proof, theorem proof. Welcome to my world. That's what a pure mathematician does all the time. State a theorem and then prove it. Now, you can see that this result is sort of two parts. There's the absolute maximum piece, and then there's the absolute minimum piece. The book handles the absolute minimum case. And so, of course, nobody's going to take the time to write them both down because they're basically similar. And you could say that if you were proving this result, you would just say, I'll do one case and then the other case is similar. Since the book does the absolute min case, I took the liberty to try to write up the proof for the absolute max case. So you could see them both. One of them's in the book and then we'll have the notes for this one. So let's do that. So we will only present here the absolute max case. We're only going to show the absolute max case in this notes, in the notes right here. Okay, well, the first thing I'm going to do right away, guys, is just immediately use the proposition we just did. So because we have exactly the same assumption, f is continuous on a closed interval, we have boundedness of continuous functions. So what I'll say here for this proof is that by proposition 4.8, f is already bounded on the closed interval AB. It is already bounded. And since I'm doing the absolute max case, this is where the the proofs will diverge slightly, but they'll be completely analogous. But then what I'm gonna do, guys, is I'm going to look at the supremum. Ooh, go back and remember something from earlier, the supremum of all of these outputs. I'm gonna call it alpha, and I'm gonna make this as a definition, so I'll use a colon equals. Colon equals to make my definition. Excuse me. The supremum of all of the f of x's. Such that x is in the closed interval AB. So this is just the least upper bound of this set. So you're looking at all of the f of x values, and you're gonna take the least upper bound of that. I'm gonna call it alpha. Now, normally, alpha could be plus infinity. However, if f is bounded on AB, then that means that all of these outputs are forming a bounded set, and that means that your least upper bound is actually in R. It's not in R sharp, it is in R. Okay, so it is in R, I'm underlining that. This is, I'll just emphasize the reason here. This is since f is bounded. The outputs of f, in other words, the range of f is bounded. So we know that this alpha is actually a real number. Okay? And you won't be surprised that I'm probably going to claim that my alpha is actually the absolute maximum value. Again, I'm ultimately going to need to come up with an x1 here, right? I'm going to have to find my absolute maximum point of the domain, but the alpha is going to be an output value that's going to actually be the absolute maximum value. So in other words, what this tells me, guys, is that f of x is less than or equal to alpha for all x in the closed interval AB. I really like these proofs because they use a lot of the stuff we've already done this semester, right? We're seeing lots of previous ideas, and right now we're talking about the supremum. By the way, of course, if we were doing the absolute min case, if you were reading the books proof, they would be working with the infimum of the set. Okay, so it's just turning everything around a little bit. Okay, so this is gonna be, guys, this alpha is gonna be my absolute maximum value, I hope. But in order for it to be such, it has to be equal to f of something, right? So that's going to be my goal, right? So we need to find, I'm just gonna kind of set up what we're gonna do next. We need to find a capital M that's also in this closed interval AB such that f of capital M is equal to alpha. That's what we need to do. We need to figure out where this capital M is. Now, of course, in your Math 150A class, you use the derivative to do it. Okay. Set the derivative equal to 0, find the critical points, and then just test them to see which one's the absolute maximum value, right? So we don't have the derivative yet. In case you're wondering, you're gonna be seeing that after spring break. And make you wait a little while longer. So we don't really have the derivative to use. This is going to be more of a non-constructive proof, by which I mean that we're not actually going to know what M is. We're just going to show that it exists, right? We're going to have to prove that it somehow that it exists. But from a practical point of view, this proof isn't going to show you how to get your absolute maximum value. So we're just proving that it exists, that f has an absolute maximum. Okay, so is everybody clear with the game plan here? Okay, so far I haven't done all that much. I've just said, look, the outputs of f are all bounded. Let's call the supremum of those values alpha. It's some real number, and my goal is to find my absolute maximum input that gives me that alpha value. Okay, so how are we going to do that? Well, as you guys know, if I subtract anything away from alpha, I no longer have an upper bound. right? Because alpha is the least upper bound of that set. So if I was to deduct anything away from alpha, then I would be able to find an f of x value larger than that. And I'm gonna actually make a whole sequence worth of such points. So what we're going to do here now is for all natural numbers n, we're gonna make a sequence, so that's where the n is coming from. We can find xn in the closed interval AB such that if we subtract 1 over n from alpha, so if we just come down a little bit, remember alpha was my least upper bound, so this is not an upper bound for my set of outputs anymore. So that means there has to be an output over here that's going to be strictly greater than that. I'm going to call it f of xn. And of course, f of xn is still less than or equal to alpha, which is my supremum. Okay, so that's what we have. And guys, the xn's are bounded. The sequence xn is bounded. So since that sequence is bounded, guess what that means? What does it mean? There's a convergent subsequence, the Bolzano-Weierstrass theorem again, twice in 20 minutes, right? We're gonna use the Bolzano-Weierstrass theorem again. So by this time, I'm just gonna say BW theorem. I'm tired of writing all those long names out. By the BW theorem, there exists a convergent subsequence. Let me call it xnk. This will be a convergent subsequence. And so here, guys, is where the whole problem is. The Bolzano-Weierstrass theorem doesn't tell you what the convergent subsequence converges to. It just says there will be, a limit to this subsequence. So we don't know what it converges to, but this is actually going to converge to the thing that we ultimately are trying to find right now, which is the m, right? It converges to m for some m in the real numbers. Actually, for some m, we can be better than that. It's in the closed interval AB. Everything's in the domain is in the closed interval AB. So guys, this is the first time we've seen the m in this proof. Over there, I might have referenced that I was going to go find an m, but I didn't actually do any work to finding it over there. This is really where it makes its appearance. The Bolzano-Weierstrass theorem guarantees that there's a convergent subsequence to these xn's that we've created. And the limit of that sequence, we're going to call it m, and we're going to claim, in fact, we're going to claim now, we're now going to claim that f of capital M is actually equal to alpha. This is going to be the claim. Well, first things first, if the convergent subsequence xnk converges to M, then by that theorem 4.1 again, f of the convergent subsequence converges to f of M, because f is continuous. So let's write that down. Since f is continuous on the entire domain, which is closed interval AB, we have that the sequence f of x and k converges to f of m. This is by that theorem 4.1 that I've already used once today as well. So these two proofs that we've done so far are both using kind of the same stuff. They're both using the same stuff. Okay. Does that make some sense? So if x and k converges to m, and as long as the function is continuous, then f of x and k converges to f of m. That's theorem 4.1. But guys, it's pretty obvious to me at least that f of x and k actually converges to something else. Because if I look at all of my f of x n's, look where they live. They're sort of less than alpha, but they're more than alpha minus n, and the alpha minus n is getting closer and closer to alpha. this sequence is squeezed, sort of literally squeezed between these two sequences. This being a constant sequence and this being a sequence that's converging to alpha as well, right? So you can almost, I mean, you literally could, you could just imagine the squeeze theorem being used here and say, here's a sequence, here's a sequence, and here's a sequence, right? And they're lined up, one is less than the next, is less than the next. And it's clear that the ones on the outside are converging to alpha, and so of course the one in the middle is converging to alpha as well. So, and therefore, if f of xn converges to alpha, then every subsequence also converges to alpha. That was another one of our theorems. Oh my gosh, we're just using everything. Right, so let's just say, since alpha minus 1 over n is less than f of xn is less than or equal to alpha, then the sequence f of xn converges to alpha. And we could just say, by the squeeze theorem, I don't even think I used that in my notes, but I think that would be a really good justification. And so thus, the sequence f, the subsequence f of x and k, of course, also has to converge to that same thing, right? Didn't we prove that? If a sequence converges, then every subsequence converges to the same thing. Yeah. So of course, that's going to be alpha in this case. So guys, look what we have. Let me put a couple boxes here. Right? And look what I'm claiming. Look what I'm claiming. I want to prove that f of m is equal to alpha. Well, what do I know? I've got my subsequence converging to alpha on the one hand, but it's converging to f of m on the other hand. So by uniqueness of limits, which is another result we had, right? So by uniqueness of limits, yeah, that's going to do it. F of capital M is equal to alpha. That's exactly right. And that's what I needed to prove. My alpha is my, that's going to be my absolute maximum value. And I've now proven that it is actually equal to f of something. So this value is actually achieved, right? This alpha value is actually, I can plug something into f that'll actually give me alpha. That's the extreme value theorem. Okay. Oh, I love it. I love this stuff. Okay. Lindsay, go ahead.
Doctor, how did we pull the alpha minus 1 of n? Is that you created the 1 of n?
I made this out of the sky, right? I sort of said, let me just subtract a little bit off of alpha so that it's no longer an upper bound for all of my f of x's. So then I can find an f of x n, in this case, that's greater than it.
Oh, got it.
Yeah, that's exactly the idea. Yeah. So we're using a little bit of the concept of supremum here again, right? The supremum of a set. Okay, let's do another one. Let me at least state this one. Maybe we'll take a short break then. And then I'll actually prove this one. This one is a very famous result. Well, all of these are pretty famous. They're actually getting better as we go. The extreme value theorem is certainly something you'll read in any calculus textbook, and this next one is too. You will see this in any book, and the thing I love about this next one is that, again, it's very easy to state it, and it makes total sense. It's not, this isn't one of these theorems that you have to rack your brain to even understand what it's saying. It's very clear what it's saying, and it's called the intermediate value theorem. So this one is a very well-known result. It's theorem 4.3. Okay, so this time we're talking about the intermediate value theorem. Okay, and again, let me just state this. Okay, so I'll state this as follows. Let's let f be a function from the closed interval a, b to r. And let's let that be continuous. Continuous on its entire domain of AB. So all three of these results today have started off with that. The function is defined on a closed interval it's continuous on that entire domain. Okay? So now we're gonna get into what this intermediate value theorem says. We're gonna make the assumption here that f of A is not the same as f of B. Okay? So in other words, those two values are different. If we now pick another value, I'll call it K. So if K, which is a real number, so if K, an element of the real numbers, is between, if it's between f of A and f of B, then what this theorem says is that K will be equal to f of something. So everything between f of A and f of B has an input that would hit that value. So then there exists a C in the real numbers such that f of C is equal to K. That's the statement. This one's a little bit more messy to write down. You do have to keep track of a C and a K and an A and a B. But it's pretty, what I actually think is helpful here is to have the picture. So let me just draw the picture and then we'll do the proof after we take a short break. But let's just draw the picture so we have some intuition going. I've got my closed interval here again, and I've got f of A is maybe here and f of B is maybe here, something like this. They're not the same. And then I pick some value of K between those two dots. Could be anywhere. So I pick a K value in there somewhere, anywhere I want between f of A and f of B. What this is saying is that if you're gonna draw this graph from this point to this point without picking up your pencil, you have to pass through that dotted line. So you have to, you have to, at some point, I guess it's right here, at least once. There could be more than one C value, but there has to be at least one input that actually hits K exactly. You can't jump over it. Of course, if f is not continuous, that wouldn't be true, right? Because if the function is not continuous, you can take big steps up and skip over some of the y-axis. But for continuous functions, you have to be able to find an input for every out. So if I was driving 50 miles an hour 1 minute, and then next minute I'm driving 70 miles an hour, then assuming I didn't really wreck my car, assuming I accelerated or decelerated in a smooth way, every single speed between 50 and 70, there was a moment in time when I was going exactly that fast. Right? Might have been just a hair of a second, right? But I have to have been doing that for at least a moment. So that's the intuition behind it. Does it make sense? This is one of those results that it makes a lot of sense of what it's saying. The proof actually is surprisingly messy. So I think to brace ourselves for that, why don't we take a short break here for 10 minutes and let you guys stretch out and get some fresh air, and then we'll pick up at about 2:20 or so.
You're back to your collar.
Does it really? Oh my gosh, sure does.
I didn't want to disrupt you in another class for it.
Thank you. So it's feeling the tension right now.
So.
It's like, what's going on back there?
So it's like. But it would help us a little bit. A little bit about subsequence between. There. Yeah. Okay. What is this? You said you took off one end, could you have taken off like anything else?
Yeah. You could have subtracted, you would need to take off something that was a function of n that's going towards 0. So you could have said alpha minus 1 over the square root of n. Or you could have said alpha minus 1 over n squared.
Just need to take off.
Just a little bit, it needs to be something that as n gets big is becoming very small. Yeah, that's all it meant, so there'd be a million things, but that's probably the easiest one.
I'll take it.
I have to pay that $20 fee to get that my stupid grade change for 71.
Oh, I haven't had to do anything for that yet.
They asked me to do a change of grading basis, so I did the paperwork.
I promise I'm not gonna get the $20.
No, they're already changed it, but they won't change it on my TDA until I pay the stupid $20. So I'm like,
That is crazy. This wasn't even your fault, right?
no, I'm so mad.
So ridiculous.
Somehow all of my classes last semester with credit, even though I put grade. I don't know.
Yeah.
So I had to like try and figure out how to change my grade. Because for 71, I need to graduate. And they're like, oh, you don't have it. I'm like, what do you mean I don't have it? Yeah.
They charge you $20.
20 bucks to change the
Absolutely,
grade.
they're charging for absolutely everything.
Right. I'm so sorry, you're gonna do paperwork for all of 5 seconds.
Right? It's your job.
It's almost 2:30, girl. You're late.
It wasn't even required, it was just
He's
MC.
gonna get fired.
I was like, what, straight off of it. What could I have done now?
No. All of them out. I think it's so stupid. That's all right, I'm just like -4.
No,
Because it's Lindsay.
kids are fucking fighting. You know, I never did the missions or this is so fucking.
No, so no matter was 16, was like, with kids like, kids are not being.
It's an obligation.
How are you planning? This one has to be with the- It's in the summer. I was like, everybody's not doing something. He's like, it might be too late. No. Well, that's going to be hard. She lost his phone, that ticket, and then Christian cried, and it's always that.
Oh, Dr. Allen, I just realized I made a really stupid mistake on the quiz.
Oh,
I'm sorry.
okay, I will forgive you, trust me, I will be just fine.
It was elementary. Okay.
These things happen.
Elementary.
I thought you were gonna say something about advising to it.
Oh yeah, I'm advising with you for the first time, actually.
It's next week, right?
Yeah, on Friday, I think.
Oh,
Friday or Thursday.
Alright,
I couldn't get any math, the teaching.
oh, I do teaching.
You do? Oh, okay, perfect, because I did it with Murphy last semester,
Uh-huh,
and he was like, oh, you should really try to get a teaching.
yeah, no, I do both.
Perfect. I was like, you know what, I've seen Dr. Allen for 2 semesters, if anyone has a good understanding of where I'm at.
I can probably do something for you.
So I had to go to advising and Dr. Soto was like, why are you here? I was like, I don't know.
They literally emailed me.
They emailed
In the
me and told me to
proposal
go.
house.
Yeah, exactly.
Is that what you were doing the other day when I saw?
Yeah, that's
Okay.
what I was doing
I didn't
yesterday.
realize I was interrupting your,
No, it's fine. I
Advising
just,
me.
I honestly, I was like, I have no reason to be here because I'm done. And he was saying the same thing. He's like, why are you doing advising? I was like, I don't know, but they keep emailing me, telling me I have to do this and they put a hold on my account.
Oh my gosh. Starting to really feel like summer out there.
Yes.
Nice and warm and, I don't know, I like it when it's kind of warm in the daytime, as long as it's cooling off at night. When we get to the later in the summer, it's like too hot all the time. But I like the contrast, it's pretty nice, so.
I think that's the Nebraska one coming out.
Yeah, probably so. You know, I'm sort of used to that. You know, they had in Lincoln, it was 85 on Monday, and then they had a blizzard warning yesterday. And they told everybody to stay home. I saw the
Oh my
pictures.
gosh.
I told my parents, you guys are staying home, right? You're not going anywhere. Oh, it's nuts. Anyway, I think we got just about everybody here. I think I'm gonna go ahead and get rolling again. So we've done what was it? Boundedness of continuous functions. We've done the extreme value theorem, and now we have the intermediate value theorem. So this is number 3. We still have several more to go. I only have a half hour, so we'll see how many of these we get to. This is the one that kind of has the messiest proof, I guess you could say. Before I do the proof, I'm just gonna give myself a bigger place to draw my number line here, guys. So that I can really try to draw a good illustration of everything. And so I'll be adding to this picture as we go along. But I'm gonna just start off with that number line from A to B. And yeah, and we have, you know, f of A is somewhere, and f of B is somewhere, maybe like this and like this. So I'll just start off with that. And then the function is, you know, kind of going somewhere to get from A to B. That's just a little bit bigger picture, a little bit easier to draw onto. So what I'm gonna do here, guys, is we do know that K is between f of A and f of B. I'm going to assume without loss of generality, so let's get the proof going here. I'm going to assume without loss of generality that f of A is less than f of B. So I'm just gonna make that as a choice. It could be that f of A is bigger than f of B. All it says here is that they're not equal. So one of them is bigger than the other. I'm just gonna make this as a assumption. The proof, if it was the other way around, would have been a more or less the same concept. So there's no reason to limit ourselves. And of course, this means that K is between that. So then f of A is less than K is less than f of B. I sometimes get people asking me the question, when it says K is between f of A and f of B, is it strictly between? Or could it be equal to the endpoints? Of course, if K is equal to either f of A or f of B, we would already be done. Because the C value could just be A or B. So it's almost not even worth mentioning that. And we might as well just assume that K is strictly between f of A and f of B. So here's the way this proof works, and it's kind of interesting. We're going to take the midpoint of A and B. So I'm gonna call that x1, and x1 is the midpoint, or in other words, the average of A and B. So we're gonna just take A plus B and divide it by 2. And somewhere here we have, actually, you know what, on my little number line here, let's just use this as our K value. I kind of like that. So K is just that horizontal line. I'm gonna pick the midpoint of A and B, which is right here. I'm gonna call that x1. So A plus B over 2. And of course, if f of x1 is equal to K, we are done with the proof. Because remember, what are we trying to prove? We're trying to prove that there is an input to the function that equals K. When you plug it into the function, you get k. Well, if f of x1 is equal to k, we're done. We would just let c be x1. So let's assume that's not the case. If that's not the case, there's a couple of possibilities. It could be that f of x1 is less than k. And in that case, what I'm gonna do is I'm gonna make an interval here, guys. I'm gonna call it I1. I'm going to let I1 be the interval from A1 to B1. I'm making a notation here. What is A1 and B1? Let me write it in words. It is the right half subinterval of the closed interval AB. That's if f of x1 is less than k. Now, in my picture, that's not true. In my picture, f of x1 is above the k line. And if that's the case, let me write down the other case as well. If f of x1 is more than k, like it is in my example from the picture, then I'm going to let I1 equals A1 comma B1. So what is A1 and B1? I'll explain that in a second. I'll show you on the picture. But in this case, we're going to take the left half subinterval of the closed interval AB. So what I'm basically saying here, guys, is that this k value is sort of playing hide and seek. It's playing hide and seek. This whole interval AB is where we're looking for the C value. It's really the C value that's playing the hide and seek. Where is C, right? And right now I'm saying, well, it's either gonna be on the left half or on the right half of the whole big interval, right? So do you agree with that? If f of x1 is bigger than k, like it is on this picture, then would you agree that the C value, the value where the function hits the k line, would be on the left half subinterval of AB, right? Whereas if my graph had stayed below this axis when it hits the x1, then you know that your C value would have been on the right half subinterval. So at least with respect to the way I've drawn the picture now, this is A1 and this is B1. And that is now my interval I1. So what you do, guys, you take your whole interval and you chop it in half. And you say, okay, my C value is either on the left side or the right side. That's kind of the way we're gonna play this game. Okay,
Brandon?
yeah.
What happens if, cause can it hit the K line twice?
It could. So that is possible, but I want to just make sure that I can guarantee that it's going to hit the K value somewhere, and which half subinterval I choose will be the interval that it is guaranteed to be in based on this information. So like in this example, f of k1 is bigger than k. It might be true that there's a C value over here on the right side as well, because this thing could wiggle a million times, right? But I do know that if f of x1 is bigger than k, I am pretty sure, and you can see it from the picture, that there will be at least one C value on the left side. I can guarantee that. The right side, I can't guarantee it. There might be some wiggles over here that cross above and below the K value, but I don't know that for sure. Here, I'm gonna know it for sure. Does that answer your question? Okay, that's a really good question. Okay, so that is sort of the first step of a long process that we're gonna use, okay? So this takes a little bit of work, right? So what we have is, we have that f of A1 is less than k, is less than f of B1. So again, you can see that on my picture, f of A1 is still here. And f of B1 is over here, right? And we can see that, oh, we said it right here, k is less than f of x1 if x1 becomes B1 in this case. Okay, so when you're in this bottom scenario, your A becomes A1 and your x1 becomes B1. Okay, so we have that, and so now what I'm gonna do is just do the same process again. I'm going to now let x2 be the average of A1 and B1. So it'll be A1 plus B1 all over 2. That would be the midpoint of I1. Okay, on this picture, that would be approximately right here, x2. So halfway between A and x1. Okay, halfway between A1 and B1. And again, if f of x2 is equal to k, we are done. Because we can just let c be equal to x2 in that case. So if we can ever write k as f of something, that's what we want to do. We're done with our proof. If there exists a point that we can plug in and get k, we're done. Okay, so if not, then we have two scenarios again. So if f of x2 is less than k, then in that case, I'm going to let I2 be equal to the interval which I'm going to define as A2 to B2. These are all closed intervals, by the way. And in this case, this is the right half subinterval of the previous interval, which was the interval from A1 to B1. Or in other words, I1. Okay, so if f of x2 was less than k, that's what we would do. Otherwise, if f of x2 is greater than k, then we're going to let I2, which again is equal to the interval A2 to B2, be the left half subinterval of the previous interval A1 to B1. This should say of, not on. Right half subinterval of the closed interval from A1 to B1. So let's look at our example again. The example really helps us to understand that. If we look at f of x2, it's right here. Is it greater than k or less than k? Greater than k. F of x2 is greater than k. So then what does it tell us to do? It says make the next interval, which I'm going to call A2 to B2, be the left half subinterval of what you had before. So here's I1. Here's I1. I'm now going to make I2 to be this left half of the previous interval. And I'm going to denote these endpoints as A2 and B2. So in this case, A2 is the same as A1, and B2 is the same as X2. Okay? And you can see again, so you still have that f of the left endpoint is less than k, and f of the right endpoint is greater than k. So you're just sort of chopping up this interval, and you're playing hide and seek with the c value. But each time you chop up the interval, the space that the c could possibly be is half as big, right? So we just keep doing this. So now, in this case, f of A2 will be less than k, will be less than f of B2. So just like before, same thing again. Same thing again. And I'm just gonna say, continuing in this manner, I assume you guys don't want me to do this all day. So, continuing in this manner. Keeping in mind that we will be stopping this process if we ever hit an xn value where f of xn equals k, we would stop at that point. But we, if not, we keep going, continuing in this manner, we obtain sequences of these a's, so I'll say a sub n and b sub n. That's right. Okay. And technically, we could think of a sub 0 as just being a itself, and b sub 0 is b itself. I guess I didn't really label that, but this a could be thought of as a naught, and b could be thought of as b naught. Okay, what I'd like you to do is notice some things about those two sequences. Looking at the a naught, a1, and a2. And then also looking at the B naught, the B1, and the B2. They have some properties. Say again?
Bounded monotone.
They're bounded and they're monotone. Absolutely right. They're absolutely right. So let's make that as a note here. That's the very next thing I wanna bring into the proof, and we know things about bounded monotone sequences, I think. So let's see if we can write this down. Note that A sub n is bounded. Why is it bounded? It's bounded because all of the values of A sub n are between A and B. The whole universe is right here, guys. There's nothing happening to the left of A or to the right of B. So of course it's bounded, and monotone increasing. So it's bounded and it's monotone increasing. Now, in this case, it's not strictly increasing. You notice A naught, A1, and A2 are all just equal to A here. But eventually, actually, if we did the X3, if we did X3 here, now our I3 interval would have been here, and this would have become A3, and this would have become B3. Notice that one of the two sequences, either the A's or the B's, stays fixed from one step to the next. Because you're chopping the interval in half, you're either taking the left half or the right half, so either the previous B value stays the same or the previous A value stays the same. So in this case, you see the A3 would have increased. So it's monotone increasing, thus converges by the monotone convergence theorem, right? Bounded monotone sequence converges. And then similarly, the sequence B sub n is bounded. But this one is monotone decreasing. But either way, doesn't really matter. It's monotone and it's bounded, so it converges. Bn converges as well. This is by the same thing, MCT. Okay, but the other thing I want you to notice is how far apart are the A's and B's? The A naught and the B naught are pretty far apart. But A1 and B1 are half as far apart as that. A2 and B2 are half as far apart as that. And A3 and B3 are half as far apart as that. And in fact, we can make another note that in general, there's actually a nice formula for this, right? How far apart, like what is the actual distance between, I'll use an absolute value bar here, I guess. What is the actual distance between one of the A ends and one of the B ends? Well, it's actually very easy. You just take the entire interval distance, which is B minus A, and you start chopping it in half according to enough powers of 2 as to how many times you did it, which would be actually n, right? So how far apart are A1 and B1? It's exactly half of B minus A, and so on and so forth. So the AN sequence converges, the BN sequence converges, something tells me they better be converging to the same thing. Because if they converge to two different things, then how in the world can the difference between them be getting, I mean, this is going to 0, right? As n goes to infinity, right? So if the AN sequence converged to one number and the BN sequence converged to a different number, right? Then somehow the difference between the ANs and BNs would have to be approaching the difference of what those limits are. But it's not, it's converging to 0 actually. Okay, so what this tells us is that thus, I'll just say it here, AN converges to X and BN converges to X. So the same X, which by the way would be in this closed interval AB for both sequences. I know this has been a little bit of a longer proof, but we are getting almost done. Finally getting almost done. It's because you have to kind of construct this whole process of how to find the C value. But that is our goal, guys. Our goal right here is to find the C value. So what we basically have, just in terms of a picture, we have A sub n converging to X, but we also have B sub n converging to X. And B sub n is kind of decreasing from the right. The A sub n sequence is sort of increasing from the left. So that's kind of visually how it would lay out. And again, we've got our picture here to kind of help us see how that works. Okay, now we also know if we, let's take a look at f of each of these things, right? If we look at f of a sub n, right? All of those values, I think it says it everywhere, right? Do you see this, guys? F of A1, it's less than K. F of A2 is less than K. F of A3, by the same reasoning, will be less than K, and so on and so on and so on. These are all less than, I'll use less than or equal to K. And similarly, the F of B1 is greater than K. F of B2 is greater than K, and so on and so on. So F of Bn is greater than or equal to K. And this is, these are sequences, but I'll just say for all n, for all natural numbers, little n. So we definitely know that. Now, there's one thing we have not used in this proof yet, guys, and that is that f itself is continuous. And we had this theorem, we've already used it twice today. Continuous functions preserve convergent sequences. So since an converges to x, guess what? F of an converges to f of x. Right? This is by theorem 4.1. I hope you don't mind, and my proof is gonna turn into a little bit of a picture now. And the f of bn is also gonna converge to x. This is also by theorem 4.1. So if bn converges to x, then f of bn has to converge to f of x. And I bet you can tell what I'm gonna be doing with that. I have this sequence less than or equal to this. I'm gonna view the k as a sequence, which is less than this sequence. The ones on the outside are converging, so guess what, guys? K has to converge to f of x, in fact. So in this case, by the squeeze theorem again, K converges to f of x. Now, when I say it converges, keep in mind K is actually a fixed number. It's not changing at all. It's given in the original statement. So of course, we also know clearly that fixed number, if I treat it as a sequence, it converges to itself. And so thus, by uniqueness of limits, I'm kind of overkilling this, guys. You know, you could pretty much just say it's clear. This whole last part of this proof is kind of clear. By uniqueness of limits, f of x is equal to k. Yeah, that's basically going to be it. And that k, that x value is actually the c that we were looking for. Yeah, so we were supposed to prove that there exists a c, and we found it. It was basically the limit of the an sequence and the bn sequence. That common value. Okay. Again, it's not a constructive proof. We never do get to find out what c is actually equal to. Even in Math 150A, you didn't do that. You don't get to find out what the c is equal to. Why not? Well, it's one of the weaknesses of the monotone convergence theorem. The monotone convergence theorem says, yeah, if your sequence is bounded and it's monotone, it'll converge, but I have no idea what it converges to. Right? So you have that, I guess, downside to some of these existence results. Just can't find the points directly. So this proof is a little messy. I'm okay with it. I'm not a huge fan of how technical it is, but it is what it is. Let's do a couple of things here that are really quick and easy that we can do in the last 7 minutes, and that is to add a couple more results to our list now. I'm going to do a corollary. This is still consequences of continuity. Corollary 4.2, and I'm going to have another descriptive name for this as well. I'm going to call this one location of roots. Location of roots. Here's what it says, guys. Let f be a function from the closed interval a, b to r. And let's let that be continuous on the closed interval a, b. So again, this is the fourth result today. They have all started out exactly the same way. Okay, what this one says is that if f of a times f of b is negative. Let's just reflect what that means. This just means that one of them's positive and one of them's negative, right? They're not both positive and they're not both negative. One is positive and one is negative. Well, then what that's gonna mean is then there exists a C in, it's actually gonna be in the open interval AB this time. With f of C equal to 0. So location of roots, a root of a function is just a number that you plug in and get 0. And again, it's a little bit of a misnomer, you don't actually find the location. Right, it just says there exists a C somewhere in that interval. But you would have seen applications of this for sure in calculus. And this one, the proof of this one is simply to use k equals 0 in the intermediate value theorem. If you guys want to abbreviate that from now on as IVT, I'm totally fine with that. The intermediate value theorem. Guys, if k is equal to 0, so if one of my f values is positive and one of them is negative, I can allow k to be 0 and it'll be between those two numbers. So this result says there exists an input that gives you 0 as an output. So that's the whole proof. I don't have to write anything else down. So that's really easy. Okay, let's do another one. It's also super fast. This one is proposition 4.9. I think I'll state it right here. Got to wrap up here with a couple more results. Proposition 4.9. This one I'm going to call the fixed point theorem. Every one of these has kind of a descriptive name, which is kind of nice. The fixed point theorem. And here's what it says. Let f be a function. This time, my function is actually going to go from the closed interval 0, 1 to the closed interval 0, 1. I'm going to assign it to be as such. I don't know why the book does that. It still could work for a closed interval AB. But the key thing is that both the domain and codomain are the same here. And they're both closed intervals. And again, I'm going to let f be continuous on that entire domain. And remember, guys, we know lots of continuous functions. Polynomials, rational functions, sines and cosines. If you add, subtract, multiply, divide, or compose continuous things, you get more continuous things. So these results we're doing today are widely applicable. This is not just some, minor application. It's like, yeah, you can use this all the time. Okay, so then what this says is there exists a point C in the closed interval 0, 1 with f of C equal to C. And just as a parenthetical thought here, such C is called a fixed point. It's called a fixed point of f. So a fixed point is one where you just plug in the number and it spits out the exact same number. Okay. This is also a very short proof, so I will just do it real quick. I have just a minute or two, but this I can do the whole proof right here. It's almost as short as the last one. Okay, obviously, if f of 0 was equal to 0, we would be done. Or if f of 1 was equal to 1, we would also be done. So let's just add that here at the beginning. If f of 0 equals 0 or f of 1 equals 1, we are done. We can just let C be either 0 or 1, if that was the case. That was drawing. But here's my little picture for this. We have the closed interval 0 to 1 here on both the x-axis and the y-axis. Right? And I'm looking for a point. I'm basically trying to find a point where the x value and the y value are the same, which means I'm trying to find a point where the graph crosses that dotted diagonal line. Okay, and if f of 0 is equal to 0, we'd already be on the line. Or if f of 1 was equal to 1, we would already be on the line. But if not, let's say that f of 0 is up here, and let's say that f of 1 is right here. All I'm trying to say is to get from the first point to the second point, I have to cross that line. It's a continuous function. So how does the write-up go? Well, what we're going to do is we assume that f of 0 does not equal 0, and f of 1 does not equal 1. I'm going to assume that those are not the fixed points. And the way we make this argument is very clever, actually. The clever way we do this is we make a new function. And I'm going to call it g of x. But the thing about g of x is it's still going to be continuous on this same domain. Because what it is it's just f of x minus x. So you already know that f is continuous. X is just a polynomial. It is certainly continuous. When we subtract continuous functions, we get a continuous function. So I'll just say which is continuous everywhere. It's continuous on the entire domain. And here, I would like to note, what is g of 0? It's f of 0 minus nothing, so that would be f of 0. By the way, f of 0 has to be positive because the outputs are all between 0 and 1. So if f of 0 is not equal to 0, then that's positive. And what about g of 1? It's the last thing, guys. We're just about there. It's just f of 1 minus 1, yeah? If I take f of 1 and I realize it's got to be f of 1 is less than 1, I subtract 1 from it, do you agree this becomes negative? So g of 0 is positive, g of 1 is negative. I feel like if I multiply g of 0 and g of 1 together, I get a negative number. So thus, g of 0 times g of 1 is negative. It's continuous, and so by the location of roots, it's the last thing. By location of roots, there exists a C in the open interval from 0 to 1, using the specific values 0 and 1 here, with g of C equal to 0. So in other words, when I plug in C right here, I get 0. But what is that? That's f of C minus C. Right? So f of C, isn't that clever? You don't actually work with f, you work with g. You construct this function g that allows you to then prove that f has a fixed. I think it's pretty nice. Oh my gosh, I feel so accomplished. I did 5 results today, and all of them are pretty spectacular. So I hope that you guys are enjoying real analysis. Study hard over the weekend for our exam and get that homework done. I can help out with that. If you need any hints or anything, let me know. And I'll send you an email with my availability, and I'll have a lot of it in the next week. So I'll be happy to grind this out with you. Have a great rest of your week. Yeah. What's fun?
Yeah, we never really would get to that. Because one of our exes is gonna hit.
Right?
I'm not following.
One of our X2s, X3, one of them's gonna hit K,
Exactly.
Oh, I see.
so then we stop.
We stopped, yes.
We never really get to that.
That's true. You certainly, but how do you know you're gonna get to that in a finite?
Not finding enough time, but
Eventually you would get there, but you really need to view it as a infinite sequence of points potentially, because, yeah, I mean, if it is finite, we can just say game over,
yeah, we never got to that.
we get the proof done. So we just assume we're never getting that to happen. If we never get that to happen, then that's where we need to begin to sequences here.
And we're trying to get to it.
Exactly. Sorry, guys, just one second. Let me just turn this off.